So we're going to start the final part of section 8.3, which is trigonometric models, application, word problems. They can be intense. Once you get the hang of it, it's not that bad. The easy part is really sketching the graph and then uh, writing the function that models that graph. The hard part is follow-up questions. So let's take a look at the first example. So we have the depth of water at the end of a pier varies with the tides throughout the day. Today, the high tide occurs at 4:15 a.m. with a depth of 5.2 meters. The low tide occurs at 10:27 a.m. with a depth of 2 meters. So our first question is to find a trigonometric equation, a function that models the depth of the water, which is defined as T hours after midnight. We'll go back to the part B and C later, but first we just have to get a sense of how we're going to do this. So when starting, if it's not already defined for you, you kind of want to define your input hours, right? Or your input value. What units is it measured in? In most cases, it's going to be time. So we're going to let T equal hours after midnight, which is 12 a.m., which means at T equals 0 hours, the time is 12 a.m. It's critical here that you think about how you want to define T. In this case, I want to define it as hours after midnight. And in some other cases, you might not want to define it as hours after midnight. You might want to define it as hours after 12 p.m. or hours after 8 a.m. You can really define it any way you want, but you want to stick with numbers that are easy to work with. So I chose a T as hours after midnight. Next thing you want to do is identify any maximum or minimum values you have in the given context within one cycle or period of the function itself. Occasionally, you might have to look for data points that are at the line of oscillation, but it's pretty rare. So right here, I'm looking at, high tide, that's a high value, maximum value is at 4:15 a.m. And then low tide here is at 12:27 a.m. with a depth of 2 meters. So I identified these two data points here. And the next thing I want to do is graph them. I'm going to sketch a graph, plot these points, sketch a curve in as well as a line of oscillation. And then from that point, once I have a visual, I want to determine should I write a sine or cosine function, right? Which one's appropriate, meaning which one is more efficient to work with. So we'll scroll over and I already have the graph kind of created, but I'll walk you through it. So when you do this, what you want to do is, I always like for my x-axis, my t-axis at this point, I want to make it long enough to give me a almost, if not more than a full period, right? So I know that I have a high point at 4.5 hours after midnight. That's 4 hours and 15 minutes, right? So you got to think about conversions now too, right? 4 hours and 15 minutes is 4.25 hours. And I have low tide at 12.45 hours after midnight again, right? So these are both in the morning. So I plot my 2 points, right? But maybe before I do that, I want to make sure I scale my x-axis appropriately, so I can at least see a wave, one full period, right? So if you think about it, 4.25 hours is a high point, and then my next low point is at 10.45 hours. This segment of the curve right here, this is only one half of the period. The second half of the period moves over to the right here. So when I sketch the scale on my axis, I definitely want to have a scale so I can, get a full picture. Notice how big it is right here. So I chose to, every blue hash mark is 3 units. So I went by threes here. So I approximated 4.25, and then on my y-axis, I approximated 5.2 meters right here. Same with my low point. And the next thing I do is I kind of sketch this section of the wave in, right? Again, this is only one half of a period. And then at that point, I move to kind of sketching what the rest of my wave would look like, right? You can get away with a sketch in this case, but you want to make it as accurate, visually as you can, so you're not deceived by your visual here. I also have this line of oscillation sketched on my graph because that's very helpful just to give yourself a visual, where's that medium line. All right, so there's no specific order in which you can do first, right? I personally like the line of oscillation value just so I know as a reference, but you could also find the period first, right? So remember to find this line of oscillation, right? You take the high point Y value and the low point Y value, so that's 5.2 and 2, and I find the average, the mean. So I'm going to add the two together and divide by 2, which I have right down here, right? 5.2 plus 2.0 divided by 2 gives me a line of oscillation at 3.6 meters. So I'll go ahead and label my 3.6 meters here. And next, because I'm working with the line of oscillation, the amplitude is helpful because that's a big piece of the equation, right? So that's the distance from the line of oscillation to the high point or to the low point here. And that's a subtraction, right? So 5.2 minus 3.6, you can see the work right down here, 5.2 minus 3.6 gives me an amplitude of 1.6. Notice that we can't define our value for A yet until we decide if we're going to deal with a sine or cosine function, okay? Next up is your period, right? The period's pretty helpful. And remember, this segment right here is only half of a period. So to find the full length of the period, what I want to do is I want to find this distance, right, for this segment of the wave right here. So that's, I need to find the distance from 4.25 hours to 10.45 hours. Subtraction, right? And then once I find that subtraction, I can double this value right here, and that'll give me the full period, right? So 10.45 hours minus 4.25 hours times 2, remember we need to double it, gives me a period of 12.4 hours. Once we have our period, it's time to move on and find your angular frequency because that's part of the function that you need to produce. So remember that the period times the angular frequency is 2 pi, and this is a good time to now identify that when we're working with these application problems, we want to always stick with radian measurements, all right? So that time unit is time in hours, but when we calculate it in the calculator, we want to work with radians, or when we produce the angular frequency here, we want to do it in terms of radians. So 12.4 times b equals 2 pi, solve for b. And I simplified this fraction to pi over 6.2. Now, I know we said let's not leave decimals and fractions. In this application setting, it's completely acceptable to do this. If you're uncomfortable with it, you can approximate if you really want to, but it's nice to have a clean piece here. So what I have right now is I have my angular frequency, B. I have my K value right here. I have my amplitude of 1.6. I need to determine my A value. And next up really is looking at the graph again and say, determining, do I want to work with a sine function or a cosine function? Because you can really work with any of them, really. This is a high point, right? It's a nice clean high point. I know both the X and Y, the input and output values here for that data point. I'm going to choose to start with a cosine function because it just makes life a lot easier. If you start with a sine functions start at the line of oscillation and increase, which means you would have to start at this point, and we don't know what this time value is for this point right here. So because of that, I don't want to work with the sine function. So I'm going to define my H value as 4.25 hours. And now that I know that I'm working with a cosine function in the standard position, I'm going to define my A value as positive, right? So now I can go down here and safely say I'm going to make A positive 1.6. I'm going to start my cosine function at a maximum value, and then I need to just generate my function here. Remember, it's A times cosine of angular frequency, which is B, times a quantity, T minus H, T for time in hours, close your groups plus K. So 1.6 times cosine of pi over 6.2 times T minus 4.25, close my groups, plus 3.6. So this is the function that models this scenario here where the tides are. And with this information, I can find additional information. For example, if I want to know the height of the tide, the depth of the tide in meters, all I have to do is plug in the number of hours after midnight into this variable t here and simplify, and I'll be able to identify the depth of the tide at that point. So we'll finish part B in a secondary video.